session with James Ratcliffe from Southampton. Talk about BPS brane intersections as meromorphic solutions.
I'm still having technical difficulties. Okay, I'm just going to use my keyboard. Yeah, so firstly, thank you very much to the organisers for giving me the opportunity to speak in front of you all. So yes, I am going to be talking to you today about BPS brane intersections as meromorphic solutions. There is a typo here, I've not introduced a new word here. So just a brief outline of the talk that I'm going to give. I'm going to try and end up at talking about BPS branes or BPS brane intersections in curved space, in particular in an AdS5 across S5 background. But some of the kind of tools and objects that will appear there will make the most sense by first kind of taking a step back and considering flat space analog, where basically a lot of the motivation and inspiration for understanding the creatures that appear here were first studied. So I'll talk about BPS brane in flat space before going on to curved space and considering a very particular example, like AdS5 plus S5 with some certain types of branes embedded. And then I will discuss how one can embed these branes via meromorphic solutions before finishing by discussing some future directions that we would like to take. Okay, so without further ado. So generically there are two types of topological defects that can be associated with branes in any kind of physically M theory or string theory. The first being spacetime defects. So when you insert a brane into some background, this will give rise to spacetime defect of your background spacetime superalgebra. And this will give rise to a central term into the supersymmetry algebra. And in particular, this will give rise to a central term in the supertranslation subalgebra of the entire superalgebra. And this is because DP branes, so I'm talking about strictly string theory here, are p-dimensional defects in superstring theories. And as I said, they will be associated with a central charge term which takes the following form, which can be associated to an identically conserved topological current. And so this central term enters the supertranslation subalgebra as follows, as a central extension. Okay, the second type of defects that can be associated to branes are defects within brane world volume theories themselves. So much like the kind of images that Neil introduced earlier and also Joe was talking about a little bit, is that when you have two branes intersecting one another from the perspective of either one of their branes, this can be understood as introducing a defect into the world volume theory of a given brane that you're looking at. So the best studied and in my opinion most illuminating examples of these types of intersections and their associated topological charges are in M theory, and this central charge, world volume central charge term here, Z, will be of particular importance to the case that I'll consider a little bit later on, but to kind of motivate these types of quantities and how they can kind of incorporate the space-time structure of this intersection, I've elected to introduce these M theory type intersections, even though my case would be in string theory. So these two central terms are associated to an M2 brane intersection, which is the Z central charge, and the string M5 brane intersection. And so these are the central terms of the world volume central algebras of these forms, but they also encode the space-time geometry of these intersections as follows. So I should say that this M2 brane intersection is two M2 branes intersecting at a point. And so from the perspective of space-time, you have one M2 brane, which I'll call the target M2 brane, and then another M2 brane which intersects this target M2 at a point. So there are two dimensions which are extending away from the target M2 brane. And this is realized by this pair of complex functions, U and U bar. Well, from the perspective of the target brane's world volume theory, this is a zero-dimensional defect, and so you integrate over the kind of co-dimensionality of of this defect. So you integrate, in this case, over the entire spatial component of the world volume. And similarly, for the string M5 brane here, we have a string exiting an M5 brane. So this would be given by a vector in the kind of ambient space, integrated over the space that is kind of tangent to the string's intersection point along the M5 brane. And so I've kind of introduced this notation here where these are 2, so the M2 brane intersection is a 2, 0 space-time form / world volume defect. And so the space-time interpretation of these intersections is realized in the following way. So if you add the dimensionality of the form plus the dimensionality of the defect, this gives you the dimensionality of the brane that is emerging from your target. So here we have a 2 + 0 brane, so an M2 brane, and then a 1 + 0, a string in this case. And so yeah, the space-time interpretation of this intersection can be realized from the world volume perspective in this manner. So that's the kind of brief overview of these types of constructions in flat space. So I should say, before I get to moving on to the curved space, so I've shown that these two charges kind of encode the space-time information of this intersection, but how can we motivate that these are also central terms? So the best way to do this is to show that they obey a BPS band. So the simplest case, and again the most analogous case to the specific brane intersection that I introduced very briefly, is this M2 brane central charge. So if you take the energy density of an M2 brane with 2 excited scalars, this U and U bar, then you notice that there are 2 equivalent ways of writing this, one with a plus and one with a minus sign. The plus sign is followed by an anti-holomorphic piece, while the minus sign is followed by a holomorphic piece. And altogether, this implies the following bound, which when integrated over the entire M2 brane world space, implies that the energy of the brane relative to its vacuum configuration is bounded from below by a quantity that is exactly this term Z. So indeed, it not only encodes the information of the space-time BPS intersection, but it is also central from the world volume. So it is also BPS, and it gives this kind of BPS condition here. So one concludes from this that this is the BPS condition for from the world volume perspective. Okay, so now that we've considered this situation in flat space, the natural thing to next consider is promoting this to curved space. So if we just recall what the supertranslation algebra gets deformed to in the presence of a DP brane, it was this. So we have the regular term proportional to the momentum here, plus this central term here, which encapsulates the contribution from the DP brane. There's a natural way of generalizing this by essentially shoving everything inside of the integral that goes into defining this central term here, and then promoting everything to a curved space analog. So that's the algorithm that one uses to generalize this to curved spaces. So a particular curved space of interest to me is AdS 5 cross S5. And in particular, I'd like to consider embedding a D7 brane into this background. So generically, the AdS 5 cross S5 metric can be written in the following form, where I've taken this redshift factor in the, so if you imagine this AdS 5 cross S5 being the near horizon limit of the D3 background, this F factor is the dominating term when you go to the near horizon limit, but generically the metric has this form. And then in preparation for embedding a D7 brane into this background, I will define a pair of holomorphic coordinates. So it will turn out that any embedding of a D7 brane into AdS 5 cross S5 can be given by any holomorphic function, or in turn, it turns out to any meromorphic function. So in preparation for that, I define this pair of complex coordinates Z and Y. And then spherically parameterize the remaining coordinates. So written in this coordinate system, the ambient metric reads as follows. Now consider inserting two D7 branes into this background along the following directions. And using the formula that I gave 2 slides ago of the curved space central term that is introduced to the world-volume supertranslation algebra, we should guess that these two branes will induce the following spacetime central charges, or central terms. And the forms of these I want you to keep in mind because these will be integral to the interpretation of meromorphic solutions in a second. So just keep the form of these in mind. So if you have a D7 brane intersection in AdS 5 process 5, then the contribution to the supertranslation algebra should be of this form. So now taking a step back, if we consider just an FD7 branes in AdS 5 process 5, parameterized by the following embedding function using the holomorphic coordinates I defined earlier, and assume no world-volume gauge field is turned on as part of the AdS. So the bosonic part of the DVI action reads as follows, where again we notice a similarity here to the M2 brane intersection, that there are two equivalent ways of writing this metric, one with a plus, one with a minus, with the plus is followed by an anti-holomorphic piece and the minus is followed by a holomorphic piece. And not only this, is that we recognize this as the sum of squares, and so one can conclude that any meromorphic or anti-meromorphic embedding function satisfies the equation of motion, or at least it minimizes the action. And indeed, we explicitly can verify that it satisfies the equation of motion too, as one would expect. And so not only are there holomorphic solutions are clearly solutions of this, or clearly minimize the action, but meromorphic solutions also, in fact, satisfy this equation of motion due to the presence of this redshift factor. So in flat space where this f is 1, this is no longer the case. However, the presence of this means that when you approach the pole of the function, this term remains finite. So meromorphic functions are indeed minimize the action, and again, we can explicitly verify that they satisfy the equations of motion. And so on shell, on either of these solutions, the DVI action becomes this. But we've seen these two quantities earlier, but the two quantities that I want you to keep in mind. And so these terms, the one and the term proportional to the derivative of the embedding function, are exactly just the central charges that one would expect from a D7 intersection. And so this interpretation of these types of embedding functions are simply a D7 bound state. And so branes along the y and y bar direction of this embedding function are interpreted as the branes that are extending along our initial NFD7 branes. And so generically, this embedding function is given by a map between Riemann surfaces, where D here is the degree of this map. And so because this is now a BPS intersection between two D7 branes, there's nothing in principle stopping us from instead considering a brane along the y and y bar directions and making an ansatz for z of y. So you can, in principle, change the perspective of what brane you're considering in this intersection. So not only this, so that was the space-time interpretation of this. Well, not only this is that we can show that they exhibit a world-volume BPS bound in an analogous manner to the M2 brane case we saw earlier. So we define the following central charge, and we showed that it obeys a BPS-like bound as before, and so we can justify that this is the right central form of the central charge of the world volume. And before we get there, because of the form of this central charge, this has a concrete understanding in terms of the Chern class of the Riemann sphere. Because this is just an integral of the curvature form over CP1. And so the central term can be understood as just the Chern class of the Riemann sphere. So this offers a concrete understanding of what this central term is computing. And so it therefore counts the maximum number of poles versus zeros of the embedding function. And so now to show that this central term is in fact central and that this embedding is BPS, density, which can be taken just from the pullback metric, is given like so. We're using the same logic that we had for the M2 brane case. The total energy obeys the following bound, where this Z is the Z that I introduced on the previous slide. And so once again, relative to the vacuum configuration, we have the following bound for the D7 brane's energy relative to its vacuum. So this central term, this Z, does enter into a BPS-like condition. Okay, so let's speed up. So we've shown that anti-meromorphic and meromorphic embeddings saturate BPS bound and satisfy the equation of motion, or at least I claim this was so. Because this is the case, we should also expect supersymmetry to be preserved. And so one can explicitly check this by imposing what's known as kappa symmetry on the brane, which I'll kind of give a whistle-stop tour of in the next slide. But the punchline of imposing kappa symmetry is that there should be an existence of killing spinors epsilon that obey this projection condition, where the killing spinors are those that remain after taking the near horizon limit, because a generic embedding will break superconformal symmetry. So these are the only killing spinors that we need to consider for a general embedding, where these gamma matrices are those that are induced on the brane. So yeah, as promised, kappa symmetry is essentially the odd part of superdiffeomorphism invariance. So if you're trying to find a superconvariant brane action, then what one does is promote everything, or promote the kind of brane action to a map between superspaces. And then in doing so, you can formulate an action which is manifestly superdiffeomorphism invariant. But the requirement of making this work is essentially what kappa invariance is. So it's the odd part of diffeomorphism invariance if you want to make an action which is not only diffeomorphism invariant, but superdiffeomorphism invariant. And so again, the punchline is this kind of projection condition, where this gamma is an embedding-dependent projection operator. So the details of this for our specific brane embedding aren't too important, but what is important is the conditions that you get out from this. So the most important one is this first condition here. And so this imposes that the killing spinor is an eigenvalue of the following two matrices, gamma 89 and gamma 23. But if it is an eigenvalue of these two, then we get BPS saturation. So in other words, supersymmetry is imposing the equation of motion, and we have supersymmetry when we get BPS saturation. So everything's self-consistent with what one might expect. While the latter, one might be concerned about the latter four equations, which impose the following constraints. So you might think that this breaks all supersymmetry. And in particular, these pairs of equations, or these sets of pairs of equations, can't mutually be imposed, so we need to kind of get rid of half of them. But we notice that these are multiplied by terms that are either holomorphic or anti-holomorphic, and so we can remove half of these by imposing, in fact, meromorphic, for the same reasons, although I've excluded an F-bar factor here, it is there, for the same reasons why the action was minimized. For meromorphic embeddings, these equations, two of these four equations vanish. But in fact, so what we get left over are these pair of equations, but in fact, these are equivalent to the two eigenvalue equations that we had that impose BPS saturation. So we get nothing new. Basically, the BPS saturation is given by a meromorphic embedding, and supersymmetry is manifest when that happens. And so these conditions will automatically be satisfied when you have a BPS saturation configuration. And because there are two constraints here on what the killing spinors need to obey, this is a quarter BPS embedding in general. So altogether, kappa